Okay, everyone, so as was mentioned, my name is Amelia Henriksen, and my presentation today is going to be discussing a lot about incorporating scientific computing into undergraduate applied math programs. So I'm here representing the Brigham Young University Applied and Computational Mathematics program. A little bit of background about myself. I started working for the program a little over a year ago. I started out as an editor who actually was writing and editing our open source lab textbooks that are in conjunction with the theory-based classrooms. And pretty quickly after that, I was promoted to the manager. So I've been working a lot with this work. The development team itself is composed of various PhD and master's and some undergraduate students. And it was really a very exciting opportunity to work with them, especially since I am actually still an undergraduate. I'll be graduating from this program in April. So to get started with a little bit, I'm going to talk about modern applied math. It's a very broad term. As I've discovered, especially in my classes, when people ask, oh, what's your major? And I'm like, oh, it's applied mathematics. What do you want to do with that? Teach? People really don't know what it's all about. So traditionally speaking, a lot of the topics that are covered in applied mathematics courses are modeling with differential equations, kind of the math of physics and engineering, which is very important, mechanics, heat transfer, fluid flow, electricity, all of those, which is great. But I think we all realize that a modern applied math class needs to include more about information science. I mean, we need interdisciplinary integration across all the scientific disciplines, not just physics and engineering. So I have here a lovely diagram. Traditionally speaking, a lot of times what happens is each of these different areas of science have a lot of math included in them. But the language that is used for this math is just different enough. There's a bit of a miscommunication there. It's like you have engineering math, and you have life science math, and you have your physics math, and all of these things are great, but without a way to integrate them all together to help our math students especially to kind of be liaisons between these different subjects, it's far less effective than it would be otherwise. And a lot of times, the way to bridge that gap to create such a beautiful mathematical science flower as we see here is to integrate scientific computation into our math classes. So just to give you a little bit of an overview of what our program is, which I'll be using as an example for some of these pedagogical techniques, you have a core curriculum of classes. So we start with a junior year of mathematical analysis and algorithm design and optimization. That's what I just finished. And then next year, I will be taking modeling with uncertainty in data and modeling with dynamics and control. Now, each of these classes is not just the theory of this. They have another class that's associated with it that is a Pythonic lab-based class. Now, these are on GitHub. They're open source. You're welcome to look at them. I have a link at the end. If you just look up BYU numerical computing, that'll get you there. So these lab classes are taking what we learn in the classroom and using fun and creative applications so that applied math classes are actually applied. Then we also have a concentration, which is a set of 4 classes that are negotiated with a different department that allows students to have some of that versatility that gives them that interdisciplinary approach to applied math. And then they also have a capstone experience. So you're either in undergraduate research or in an internship program for the summer between your junior and senior years. For example, my concentration is biostatistics, and right now I'm doing research in using fractal geometry to model prosthetic implants. So I cannot discuss all of the topics that we cover in our labs. There are too many. It would be completely impractical in a presentation of this length. However, I can talk about some of the basic concepts using these labs as examples behind what you want to do when you're incorporating Python into the classroom, especially a lab-based classroom. So the first one is fostering student interest. Students need to be interested in what you're doing. If you have that disconnect between the class and real-world experiences, there's really no motivation. So a really good example of this is one of our labs. It's filtering and convolution. So the first thing that you do is you have a a speech from FDR, and what you do is it's really noisy, you can't hear what it is. You use the inverse discrete Fourier transform, and then you can cancel out that, and you get to find out what was being said. After that, we actually take a balloon pop in an auditorium, and then we take a piano played in a dead room. We take those two sounds, we convolve them, and then it sounds like the piano is being played in the auditorium. That was a really fun lab, and a lot of the students afterwards actually enjoyed it so much that they took a lot of other recordings and they were convolving them and kind of experimenting on their own. And this is obviously, as teachers, exactly what we want. We want the students to be interested enough to go outside of the classroom and do this on their own. Another really important part, and this is extremely important for a math curriculum, is theoretical versus implementable algorithms. So, theoretical algorithms are often extremely helpful for establishing proofs. They're very elegant. They are excellent for a theoretical classroom, and they need to be addressed. However, sometimes they're not useful outside of just doing things by hand, and as we know, we can't just do everything by hand. That's not practical in real-world applications, and so we need to be teaching our undergraduates some of the pitfalls of theoretical algorithms and the way to fix them. So one of the labs that we have is about QR decomposition, which obviously we can use for least squares methods, which can solve our systems of equations in a far more stable manner than Gaussian elimination, which is not stable. There are quite a few labs like that that deal with stability and kind of show the contrast for when things break down. Another one that's really important to address is pseudospectral methods for PDEs. We have 2 labs on pseudospectral methods, and they are a lot better than some of the explicit classroom-taught methods. Another thing that we need to address, we need to go beyond Newton's method when we're teaching undergraduates optimization. So here are a couple of things that we cover. For example, CVXOpt. Great tool to start teaching students how to use this optimization. Newton's method is awesome. It's really easy to prove that the convergence is quadratic. But inverting Hessian matrices is unstable, and you need to teach students BFGS. You need to teach them quasi-Newton methods. You need to teach them line search, and we have a lab on line search where we show where Newton's method breaks down, and then give them the tools to learn these other algorithms. Another thing about a Python-based lab class is it allows the students to better understand how to code these algorithms, because coding it is the way where you cannot make mistakes or your computer will yell at you. And you learn these algorithms really well. Simplex, that's a lab that we have that's really, really good for that. Because not only can you show where it degenerates, but you can show how to fix it using Bland's rule. And that way the students progress not only in the math classroom, but in the application thereof. Another one that I personally really like, this is one of our posters. It's a bit of a joke from one of my friends that claims that we have infinite cake. We do not have infinite cake, but we do solve the finite and infinite horizon cake eating problems in class, because dynamic optimization is something that really needs to be addressed. And then we have a multi-armed bandit lab. That was one of the most fun labs that we had there, and I would encourage you to check it out. Models versus modeling. Model, that's a noun. Modeling, that's a verb. We need to do the latter. Teaching models is very important. However, models, like algorithms, because they often are, break down. And one of the important things about modeling labs is you need to show a couple of these. You need to show that finding a solution versus finding the correct solution are 2 entirely different things. And this is something that undergraduates, to be very frank, often don't know. You need to point this out to them. And so boundary value problems, that is a really good way to show them that there are many solutions, but that doesn't mean that they're necessarily correct. So that's something we definitely address in our labs. You need to build up on these models, and then you need to break them down. That's where you start introducing data. It's extremely, extremely important. And while we're introducing data, we need to model with uncertainty in data. So this is a section of the labs that I have not addressed as much personally. I've worked with it, obviously, as the manager, but I haven't taken the math-based classes. However, I can tell you that we have a lot of really valuable introductions to Spark, MongoDB, NPI, SQL, regular expressions, things like that. undergraduates are not going to become experts in these fields, but they need to be introduced to them. And these labs are a really excellent way to get the ball rolling in that direction so that they have a foundation before they go on to graduate work. And then obviously these are some of the 4 topics that are most heavily focused on in our volume 3. So measure theoretic probability, stochastic processes, Bayesian statistics, and machine learning. All of those are part of that very fundamental area of information science that needs to be addressed in conjunction with some of the more typical ODEs and PDEs that we use in the classroom. However, on the importance of ODEs and PDEs, we do have a lot of very cool examples of things that we do here. Here are a couple of my favorites, the SIR and SEIR models. If you don't know what that is, it's disease modeling. So susceptible, infected, and recovered, or susceptible, exposed, infected, and recovered. As I mentioned before, my concentration is in biostatistics. I just took a class in epidemiology, so I'm really looking forward to actually doing this lab because it relates directly to what I did. And there you see that the students have this integration across the disciplines because, oh, I took this class, I learned about that. Oh, this is how you actually do it in applied math class. And that gives them the tools to be the kind of versatile students and workers that we need in a modern world. Another really fun one is our traveling waves lab, which we use to model interacting solitons. One of my PhD students, that's his area of research. And so they're modeling this interaction, and it's very, very cool. And as we mentioned before, that fosters student interest. Sometimes undergraduate programs are a little bit afraid to go into too scary of modeling because, after all, they are just undergrads. However, having real-world motivation actually makes undergrads be able to do a lot of things that you might think they couldn't. And we've definitely proved that in our program. Another one that's really cool that I haven't had a lot to do with, but my professor who is in the health industry does, is the weight change model, which has a lot of really cool healthcare data that they work with there. So outside of just the lab classes, you need to have a comprehensive and balanced approach to what you're doing. So the important thing to remember is that you need to foster the students. You need to invest in them. They are undergraduates. They need to learn how to work together. So what BYU has done is they have actually created a lockstep cohort. So there are 2 important things here, the lockstep and the cohort. The lockstep obviously implies that they are taking these classes at set times with set people with set professors. This is great for the professors because it means that they know what the other teacher is taught and can work off of that. So often in math classes, there's almost a cafeteria-style approach. You go up to a class and you take some of that, and then the other class doesn't know if you've taken that class or not, so they have to address a little of this and they have to address a little of that. Having a lockstep cohort means that you're very, very focused in how you are addressing these topics and you know what the students know, which means that you don't waste any time. Having a cohort structure facilitates not only a lot of fast friendships, but collaborative abilities. Now, I don't know about any of your programs, but personally for me, most of the mathematicians that I have met are kind of lone wolves. They don't like working in groups. They feel they do better alone. But you don't just work alone in a big problem. You need to be able to collaborate. And so creating a lockstep cohort is what facilitates that collaborative skill that is so important in industry and academia. Another 2 things that I wanted to highlight a little bit more is the capstone experience and the concentration classes. So the capstone experience is required. And obviously we can teach a lot in the classrooms, but students need to actually get out into the real world and start solving these problems, learning how to network, all of those important skills that will prepare them either to go straight into industry from their undergraduate degree or be able to be working through their master's degree and have that motivation that really helps with those abstract concepts. As I mentioned before, my capstone experience is in research right now. And it's been an absolutely fantastic experience because I've been able to work with this biomedical data. The concentration classes, there are a choice of over 20, and that is growing. Students are able to pick what they want to do with their math. They're no longer just, you have to do this, and this is the area of research that I do, but they get to approach other professors, learn from them, because obviously the math professors are not the only ones who know how to do math. So Just in conclusion, I'd like to thank some of the head professors of this program, which are Dr. Jeff Humphreys, Dr. Tylee Jarvis, and also Dr. Emily Evans, the entire Acme development team, Brigham Young University, the SciPy 2015 conference, and all of you. Thank you so much for listening. And if you'd like to learn more, please visit our website at acme.byu.edu. And our labs are available at this GitHub. Thank you very much. Do you have any questions?
So I have a question.
Yes.
Is this program targeted just to the applied math majors, or is it also open for those who may be interested in at least learning some aspects of this in their particular major?
Right, so obviously these classes are available to anyone who wants to take them. However, the applied math program itself is very rigorous. We have a couple of double majors in there, and we've had a lot of people come from different engineering backgrounds, biology backgrounds, and that kind of thing. But generally speaking, those alternate interests are taken care of in the concentration classes. All right. Yes?
So, I guess more from an organizational
Mm-hmm.
Did you approach other departments at BYU in order to get their buy-in to this program? I'm just wondering how you were able to come up with all these different possible capstone experiences for students.
Exactly, and yes, the answer is yes, we did. So with the concentration section, we approached each of the departments that we wanted to add a concentration for and worked with them to figure out a series of classes that would be rigorous, that would incorporate a lot of the math that we were learning, and that would give them the experiences they needed. And we went to the departments and asked what they felt those experiences that they needed to kind of be able to move forward with that subject was. With the capstone experience, with the internships, we've done a lot of networking outside of our school, obviously, and in research, yes, there are several people in different departments for their research, and we try to have a lot of versatility there.
How long has this program been in development?
It's been in development for just a couple of years. We're the pilot program, and we're being funded by an NSF grant.
That's pretty amazing. In just a couple of years, yeah.
Yeah, it's been a bit of a whirlwind, but it's been very, very fun. Any other questions?
All right, well, thanks again. Very good presentation.
Thank you